This is part one of the notes on redox reactions. In this video, we are going to talk about assigning oxidation numbers and what redox reactions are. It will be helpful to have a periodic table available throughout these notes. So what is a redox reaction? A redox reaction is a type of reaction where high energy electrons are transferred from one substance to another so that the electrons move to a lower energy state, resulting in the release of energy. And there are two parts of a redox reaction, and that's where this name comes from. One substance is losing electrons, which is called oxidation. And so that's where the second half of that redox name comes from. And at the same time, one substance is gaining electrons, which is called reduction. And so through that reduction and oxidation, we get redox reactions. Only 4 of our 5 types of reactions are going to be redox reactions: single displacement, combustion, synthesis, and decomposition. We will look at at the last example in these notes why double displacement reactions are not redox reactions. Another way to look at how this is happening, and we might consider maybe an example where we're looking at, let's say, aluminum plus nitrogen, and then that is going to produce aluminum nitride. And so if we notice here, aluminum has a neutral charge. Aluminum in this case has 13 electrons, and nitrogen has 7 electrons. Through, though, this formation of an ionic compound, aluminum has 3 valence electrons, nitrogen has 5, and through forming that compound, aluminum ends up losing 3 electrons, so it ends up with 10 electrons, and nitrogen is gaining 3 electrons, so it's going to end up with 10 as well. And so as we look at this, if aluminum is our chemical A in something like this, aluminum is that A. That A then, by losing electrons, aluminum has a positive charge, and that loss of electrons is called oxidation. So we would say aluminum is oxidized for B. This B would be our nitrogen. So nitrogen started neutral, but through that gaining of electrons, so that now nitrogen had that -3 charge, it is reduced. So that's what's happening. And in order to figure this out, we have a couple things to help us remember what reduction and oxidation mean. And we're going to look at how we can determine what is happening if we're looking at just a general equation. So oxidation, the definition of oxidation is that when a substance loses electrons in a reaction. The definition of reduction is when a substance is gaining electrons through a reaction. There are 2 ways to help us remember this, 2 acronyms. Leo says GER is one of those, so losing electrons is oxidation, gaining electrons is reduction. Oil rig is another thing you can use to remember that. Oxidation is loss, reduction is gain, and remember we're talking about electrons here. So we're going to come back to remembering these acronyms as we start to identify what is reduced or oxidized through a reaction. We also use oxidation numbers to help us determine what is reduced or oxidized, because it's not easy to see where electrons are moving when we are looking at a chemical reaction. So oxidation numbers help us determine how those electrons move. And if we think back to that example, that aluminum plus nitrogen forming aluminum nitride, in that, what happens to charge if electrons are lost? Well, aluminum loses its 3 electrons in that ionic compound, and so aluminum is going to have a +3 charge. By losing those electrons, the charge goes up or becomes more positive. And what happens to the charge if electrons are gained? Well, nitrogen is gaining electrons. It's gaining 3. So nitrogen went from being neutral to having a charge of -3. So if electrons are gained, charge goes down or becomes more negative. And so oxidation numbers are very much related to charge, but they are a little bit different. Oxidation, and that's what it talks about on this next slide. So oxidation numbers, these are also called oxidation states because it's talking about those high-low energy states. We're going to just refer to them as oxidation numbers. An oxidation number is a number that tells us how many electrons something is going to lose and how many electrons something is going to gain in the reaction. Oxidation numbers are hypothetical charges that an atom would have if all the bonds in the compound are ionic. And so we're going to see if we look at maybe a covalent compound or a polyatomic ion. Those are covalently shared electrons. Oxidation numbers, we assume everything's ionic, and then our rules kind of tell us what that hypothetical charge would be. Oftentimes, oxidation numbers are the same as normal charge of an atom. We are going to see variations in oxidation numbers for nonmetals such as nitrogen, phosphorus, and sulfur. And so those are kind of our most common times that we see those oxidation numbers maybe differing from the charge we think they would have. And so then these are going to help us determine what's being oxidized, losing electrons, and what is being reduced, gaining electrons, as we compare oxidation numbers from before the reaction to after. There are 9 rules for assigning oxidation numbers. I'm going to go through these, but feel free to pause the video and read through them a little bit more slowly if you need. The oxidation number of any free element is 0, so if you have in a reaction something by itself, that oxidation number is 0 because that didn't gain or lose any electrons. Number 2, the oxidation number of any monatomic, an atom by itself, ion is equal to its charge. So if we look at these examples here, we don't often see these in the reactions that we are writing, but that is what we that is how we determine those. The more electronegative element in a binary 2 compound will take its normal charge from the periodic table as its oxidation number. So if we look at this compound copper oxide, well, oxygen is most electronegative, so it is going to take its charge of -2. We could then figure out what copper's charge is. Copper is a transition metal, so we would need to figure out its charge and its oxidation number based on oxygen. Based on Rule 8, we can determine that that is +2, but we'll talk about Rule 8 a little bit later. One other thing to note, you do not have to memorize what number each rule is. You just have to be able to apply these rules and assign oxidation numbers for an entire reaction. All right, moving on to Rule 4. The oxidation number of fluorine in a compound is always -1. Fluorine is our most electronegative element. And so again, the more electronegative element in a compound is going to take its normal charge. Fluorine is always going to be a -1. And again, based on Rule 8, we could figure out in this case that copper is going to be a +1 based on that. So some of these rules are telling us what we should start with assigning oxidation numbers for in our compound. Number 5, simple metals have their predictable normal charge as their oxidation number. So columns 1 and 2 on our periodic table, we know those always have a specific charge. So those are going to have an oxidation number that is the same as that. And then same thing with aluminum +3. Oxygen, Rule 6, oxygen has a -2 charge or oxidation number with one exception. So usually if we look at Na2O, oxygen is more electronegative. It has a -2 charge and -2 oxidation number. The exception is that in a peroxide is if you have 2 of some element and 2 oxygens, oxygen is going to have a -1 charge or oxidation number. And so hydrogen peroxide is H2O2. Oxygen is going to have a -1 oxidation number in that case, and then hydrogen would be a +1. All right, and we've kind of seen some things here for 7 and 8. I've referenced these a little bit. Hydrogen can do two things. It has a split personality. So when hydrogen is with a metal, hydrogen's oxidation number is going to be -1. When hydrogen is with a nonmetal, hydrogen's oxidation number is a +1. And so we saw that up here with this peroxide of hydrogen with oxygen. Oxygen is a nonmetal, and so that's why hydrogen had that +1 oxidation number. So we have 2 hydrogens with a +1 oxidation number, 2 oxygens with a -1 oxidation number. And again, we're going to reference Rule 8. That shows us that works out how we need it to. And so here's an example. Magnesium with hydrogen. Hydrogen would have a -1 oxidation number. NH3, oxygen would have a +1 oxidation number. And so why can I maybe determine some of these things? And I've referenced Rule 8 in a couple of the other examples. And this one is one we're going to kind of use the most, and this is a good check that we applied our rules correctly. The sum of the oxidation numbers in a neutral compound must be equal to 0. And so if we look at any of these that kind of referenced Rule 8 before, so if I look at this one right here, fluorine is always a -1. Well, copper has to be a +1. I have 1 fluorine and I have 1 copper. If this is -1, that copper is going to have a +1, so that the total oxidation numbers for those is 0. Same thing down here. Oxygen has a -2 oxidation number, and we have oxygen, just one of those. Well, we have 2 sodiums. Each sodium has a +1, so 2 times +1 is +2. And then if we add -2, that's a total of 0. And so Rule 8, the sum of the neutral compound must equal 0. That is what kind of helps us figure out oxidation numbers on different things. All of our rules are going to need to work together. How we're going to really use this rule is when we're dealing with some of those elements like phosphorus, nitrogen, and sulfur, where their oxidation numbers are going to vary. And those are kind of the 3 common ones where those are going to vary. And then the last rule, and hopefully this makes sense with a couple of things we've talked about, the sum of the oxidation numbers in a polyatomic ion must be equal to the typical charge on that polyatomic ion. And so if we look at nitrate NO3 with a -1 charge, well, one nitrogen plus the oxidation number for 3 oxygens, those are going to equal those are going to all have to add together to equal that -1. For sulfate, those are going to have to add together to equal -2. So feel free to reference the rules as we go through these. Again, you do not have to memorize what each rule is. I'm going to kind of, as we go through these, make a note of what rule I'm referencing as we practice assigning oxidation numbers. And again, it's going to be helpful to have a periodic table so that you can look up charges if you don't know what they are. All right, so with this has the first element, so we're going to put like chlorine in here. Once we get to this NH3, nitrogen's going to go here and hydrogen's going to go there, so kind of just the order they're listed in the compound. So first one, Cl2, well, this one referenced by rule number 1 is that anything that is a free element and is neutral is going to have an oxidation number of 0. Number 2, chlorine with a -1 charge. Well, rule 2 said any monatomic, any ion by itself, is going to have an oxidation number of -1. So it's going to match that charge there. And again, that makes sense, or should make sense, because our oxidation number is telling us how many electrons were gained. If you are gaining electrons, then you're going to have a negative charge. NH3. As we look at this one, we have 2 of these that we need to look at. And so what rule are we going to apply first? Well, I see that I have a hydrogen. If I go back to my rule number 7, hydrogen is with a nonmetal, which means hydrogen's going to have a +1 oxidation number. And so I'm going to use reference that rule 7. So because hydrogen is with a nonmetal, it is going to be a +1. Then, as we look at this, my rule number 8, I know that these have to add to give me that 0. Well, I have 3 hydrogens, and so that is a +3 from my hydrogens. So my nitrogen is going to have to get me back to a total of 0 for that neutral compound. And so that makes our nitrogen a -3 for that oxidation number, because the total has to add to 0. One thing to note is that if we have multiple hydrogens, this number is just referencing the oxidation number of one hydrogen, of each hydrogen. So we take into account those subscripts when we're finding the total of those oxidation states for each compound. All right, on to our next one, CaH2. And again, we always know with these that that total for the compound is going to equal 0. But we want to think of, okay, where can we start? And all of your rules should work together. You might notice that, okay, hydrogen is now with a metal, which means it's going to have an oxidation number of -1. And so you could start there because that is with a metal. But we could also start with the fact that calcium is a technically, quote, simple metal. We always know what calcium's charge is, and oxidation numbers are referencing that charge. So that calcium is going to be a +2 because it is a simple metal, which is referenced in rule number 5. We can make sure and check that rule 8 works, that the total is going to equal 0. We have 1 calcium with a +2, and then we have 2 hydrogens, each one with a -1, and so that does equal that total of 0, and so rule 8 is fulfilled as well. If you're feeling like you want to try the next couple on your own, go for it. Otherwise, I'm going to keep talking through. All right, Na2O2. We can start a couple places. We know that the total for these is going to have to equal 0. This is a special case, though. If you just assume oxygen is -2 and sodium is +1 because sodium is a simple metal, well, then we're going to get 2 times +1 plus 2 times -2, because we have 2 oxygens and each has a -2. This, though, doesn't add up to 0. This is going to give me a total of -2, and so something that I wrote is incorrect. And so we don't see these a ton, but one thing to note is that Na2O2 is a peroxide. Anytime you have 2 of one element and 2 oxygens, that's a peroxide. And so our rule for oxygens in a peroxide is, this is our exception. Oxygen is going to have a -1 charge or oxidation number when it is in a peroxide. And so that fixes our problem because that's going to be a -1. This is a peroxide, so that's rule 6, talks about peroxides. And then that fulfills what we need. We have 2 sodiums with each being a +1, so that's a +2. We have 2 oxygens, each with a -1, that's -2, so that gives us our total of 0 for the compound. All right, next one, K3PO4. Well, by rule 8, we know that the total has to equal 0 for our compound, so we need to pick a place to start. We might pick our oxygen. Oxygen is always -2, unless it's in a peroxide. This one's not a peroxide, so we know that's -2. I also can look at my PO4 group. That whole group has to add to -3 because of that charge, so I could use that. Potassium is also a simple metal, and so I also know that that potassium is going to be a +1 because it is a simple metal. And so we can kind of, whatever you recognize first can be helpful. If maybe you forgot your charge for phosphate, if we see we have potassium, which is simple metal, so we know it's a +1, and I have 3 of those, Well, this gives me a positive 3. That entire PO4 group then is going to have to carry a negative 3 total in order for us to get to that 0. And remember, it's rule number 9 that talks about our polyatomics have to add to the charge for that polyatomic. And because we know oxygen is -2, we can now use oxygen to find phosphorus. And remember those common elements that will change. Nitrogen is often changing, phosphorus and sulfur. Those are the 3 that we often see changing. And so we see those ones are going to have kind of varied oxidation numbers. So let's use what we know. We have 4 oxygens. Each oxygen is a -2, so that's a total of -8. So I need to figure out what's going to make this true. So what a -8 is going to give me a -3? Well, phosphorus needs to carry that +5 oxidation number in order for us to have 5 - 8 giving us that -3 for that. So that phosphorus is going to be a -3 on those. We also, for our looking back at our total, you can go back and check and make sure, does my total add to 0 like I expect it to? Well, I've got 3 times +1 plus I've got 1 plus 5 plus I have 4 times -2. So that's 3 plus 5 minus 8. That gives me 0, so that's a good check that I did everything correctly on that one. All right, next one, CuNO32. We've got so copper nitrate. This one before we knew potassium had a +1. Copper, though, is a transition metal, so its charge is going to depend on what else it's paired with. So we're going to actually need to use this information for our polyatomic to determine copper's charge and copper's oxidation number. So looking at this NO32, well, I know that nitrate, each nitrate group, NO3, is a -1 charge. If I have 2 NO3s, that means that my copper is going to have to carry +2 in order to get that to be a total of 0 for the compound. So we can use those polyatomic charges, and we need to use those charges to find oxidation numbers for transition metals in neutral compounds. Then we can treat this nitrate just like we did with our phosphate up here. Looking at that NO3, well, oxygen has to be -2 by rule 6 because it's not in a peroxide. And so then if I have 3 oxygens, well, that's a 3 times -2, that's a -6. -6 and what is going to give me a -1. So in this case, we have a +5 for our nitrogen based on what we needed to get that polyatomic fulfilled. And again, we should be able to look at this and add those up, adding up all of our oxidation numbers based on our compound to get a total of 0. All right, last one on here, we've got NH4Cl. Looking at this, our NH4, that is our one polyatomic that has a +1 charge. So we can use that to figure out our nitrogens and our hydrogens. Chlorine is our most electronegative element in here, so it's going to have the same charge that it normally would have. And then we can start to figure those other pieces out. So we found our chlorine. Hydrogen, we have a rule. It's either +1 or -1. So we need to think back to our rule. Rule 7, this is our hydrogen is with nonmetals, which means it's going to be a +1. And then we're going to determine nitrogen, which is our less electronegative of all of those. We're going to have to determine nitrogen from those other pieces. And again, you can look at this group as a whole compound equaling 0, or you can just look at that NH4 needing to add up to 1. Well, if this whole group has to add up to 1 and I have 4 hydrogens, my hydrogens are equal to +4. My total needs to equal +1. So if I have +4, I need +1, my nitrogen is going to have to be a -3 in that case, so that the total compound gets to 0 and so that my polyatomic adds to the charge of that polyatomic. So these are kind of like puzzles. You have to apply your rules, and it's things like transition metals and some of those nonmetals like nitrogen, phosphorus, and sulfur, that those oxidation numbers can change depending on what they are paired with. This is the end of the first video. Feel free to continue the notes in video 2.